Good morning. Being the recipient of the Supleco AOCS Research Award is certainly a great honor, as the previous recipients are all world-class leaders in lipid research. Being in such company is truly humbling, and I have to thank the many colleagues, students, postdocs, research assistants, and technicians who have all helped me reach this point in my long career. No less is the tremendous support from my wife, who has tolerated my work schedule over the past half-century. It's very hard to cover a lot of research in 30 to 40 minutes, so I will try to highlight some of the work conducted during the past half-century on canola and what I'm continuing at the present time. The outline will be a background, how I landed here, my early work on lipases and lipoxygenases, my sabbatical and titanium tetrachloride, bucket chemistry and the new Rancidity test, my introduction to rapeseed and canola, sedimentation, minor components and the use of the IATRA scan, and canola phenols or Canola, and a conclusion. After graduating from Moseley Grammar School in Birmingham, England in 1960, and I still keep in touch with colleague friends there, I completed a degree in biochemistry and a PhD in toxicology at the University of Birmingham. I then taught for 2 years in the Department of Biology and Food Science in London, England, at what is now the South Bank University. And in 1968, I accepted an invitation to join the Department of Foods and Nutrition at the University of Manitoba. My initial research was on lipoxygenases and lipases, initially focused on fava bean because that was a crop that was being highly promoted at that time by the Dean of the Faculty of Agriculture, although we did look at other crops, including peas and lupins. I worked with my late colleague, Dr. Michael Henderson, with whom I wrote my first book. It was during my sabbatical in Israel at the Hebrew University Faculty of Agriculture in Rehovot that was pivotal in determining the future direction of my research. I met and collaborated with Professor Chaim Frankel, a plant scientist from the Rutgers University, who was also on sabbatical, at the VOLCANI Center, and we were looking at the aging of plants. He was measuring inorganic peroxides using titanium tetrachloride. As in geology, inorganic peroxides were used to detect titanium in rocks. I wondered whether it would also measure organic peroxides. So I set up a lipoxygenase experiment, which confirmed this. I should point out this was still the time of the fun age of bucket chemistry. So the question was asked, could this be a basis for a new method for measuring rancidity? On my return, I immediately ordered titanium tetrachloride, made it up in a 20% solution in concentrated hydrochloric acid, which was certainly had to be done carefully in the fume hood, and then reacted it with a variety of organic peroxides and organic hydroperoxides. To my surprise, it only reacted with organic hydroperoxides, forming a complex with a definite peak at a broad peak at 415 nanometers. This could be measured spectrophotometrically, since hydroperoxides are the first compounds formed during rancidity. So I set up a Charles oven test at 65 degrees using rapeseed oil, not fully appreciating that this was the new low erucic acid variety developed at the University of Manitoba by Dr. Baldur Stephenson, the plant breeder. The paper was accepted for publication and was the first one I published in the Journal of the American Chemists Society. An interesting comment by one of the reviewers was, "Why on earth did you do this on rapeseed oil? It isn't even edible." Well, times have certainly changed. The method was very simple. It required dissolving half a ml of oil in 10 mL of acetone, adding half a ml of the titanium reagent carefully, mixing and adding 2 mL of concentrated ammonium hydroxide. You get formation of a titanium complex which forms a precipitate, and the mixture was centrifuged and the supernatant discarded very carefully. The precipitate was then dissolved in 4 normal nitric acid, and the absorbance read at 415 nanometers. This is an example of the Charlotte test, where the first one is the control going up to the 16 days, which is the hydroperoxide formation. And there again, this is the example of the absorbance spectra. So there again, you get blank, and then you get the development of the 415 after 16 days at 65 degrees centigrade. The hydroperoxide method proved extremely reliable, correlated well with both peroxide and TBA values, as well as odor intensity values. It was a very fast method, and you could do a lot of samples with the solutions being very stable. Now, I realized this wasn't green chemistry, but I will discuss later a method we developed almost 40 years later. People who came into the lab loved it, and no endpoint was required, like titrating for the peroxide value, and it was very successful. In fact, titanium tetrachloride, which eventually we called tickle form, I used it to react with a whole range of different compounds. Obviously, initially I had hydrogen peroxide, measure inorganic hydrogen peroxide in dairy products that are used to make various products, and you want to get rid of the used peroxide to get rid of the pathogens, and then you need to get rid of that hydrogen peroxide to further develop. So we developed that method. Lipid hydroperoxides, of course, in the Rancidity method. Phenolics, particularly chlorogenic acid, was a very useful method. Vicine and convicine, which are in favor of them since we were working on the faba beans, and worked out extremely well, and synapine, which we used effectively measuring synapine. We published about 10 papers, including 2 in Journal of Chromatography, because we could use it as a spray to differentiate between the ozone dihydroxyphenolics. During this time, I was privileged to work with a wonderful colleague and mentor, the late Professor Marion Vasey-Genzel, a sensory specialist who introduced me to rapeseed and canola, and together we established the properties, behavior, performance of rapeseed oil that facilitated its transition from rapeseed to canola oil. Our work led to many papers and reports, and the publication of the first booklet on canola oil. This was commissioned by the Canola Council of Canada, and it went through a number of revisions and translations, and this was part of a successful strategy to launch canola oil worldwide as an excellent, healthy, edible oil for human consumption. In fact, the latest edition in 1989 was considered so good that it was used in a graduate course on lipids at the University of California at Davis. Now, canola oil, being very high in polyunsaturated fatty acids, that is high in linoleic acid, 22%, and linolenic, more than 10%, readily oxidized during frying. So we examined a new linolenic acid canola oil, Stellar, that was also developed at the University of Manitoba by Rachel Scarth and the late Baldur Stephenson. And we collaborated with Roy Carr at POS Saskatoon, who processed it. And the paper was published in Lebensmittelwissenschaft, which of course changed to a new journal, and in 1993, and it showed a substantial improvement in the stability of stellar canola oil over the regular canola oil. And this really shows the Stella had a reduced linolenic acid, slightly higher linoleic, slightly higher oleic. And of course, looking at the carbonyl and dienol, which is a method developed by colleague Dr. Jabilski, you can see on the top, the dark is the regular canola oil, and on the bottom is the West Star, the West Star, and you can see how much more stable it is. Also, in terms of the odor pleasantness, you can see that this was done by a taste panel, and you can see that very little change during that. This was a Charlevin at 60 degrees and was much, much improved. And in fact, this was subsequently selected by a large commercial food manufacturer in Canada. Nevertheless, in North America, oils were traditionally hydrogenated for frying, as well as in the production of baking fats and margarines. This differed from Europe, where they used interesterification, and unfortunately, hydrogenation produced trans fats, and sadly, it took half a century before they were banned by the FDA, in spite of early evidence of health concerns raised half a century ago by the late Professor Fred Kummerow, who actually, at the age of 100, took FDA to court and won it just a few years before he passed away. I did a little bit of work on high oleic canola oil, but I won't be talking much about that here. This led to the phenomena of sedimentation. This was an interesting phenomena that occurred in canola oil in the 1990s. The sediment formed, and that sort of shook up the industry. Sediment formation, we know, was well known to occur in cottonseed and sunflower oils, as they are both rich in waxes and high melting lipids, which precipitate at low temperatures, forming a haze. Canola oil had previously demonstrated excellent cold temperature stability due to it being very low in saturated lipids. However, this serious sedimentation problem occurred in canola oil, and I was contacted by the late Jim Dawn, who started looking at this problem, but wondered whether I would be interested in continuing this work, as Grain Research Labs didn't have the mandate to examine this phenomena. I quickly pulled together a team of researchers, Dr. Kostas Bilideros and Dr. Roman Jabilski, and with a strategic grant from NSERC, we hired a postdoc. The first and important step was to isolate the sediment from the affected hazy canola oil. This was a challenge due to its low content of less than 100 parts per million, but we obtained a sediment by double extraction of the filter cake with boiling chloroform and precipitated at low temperature. The residual oil was removed with petroleum ether, and we were able to get a significant amount of sediment to work with. In the meantime, we visited a processing plant in Morden, Manitoba, in which canola was processed, but previously they processed sunflower, and they still used the winterization process, even with canola. So we went there, and to our surprise, we came back with a lot of sediment material that proved to be identical with the material we isolated from the bottle. A typical composition of is shown in this slide, where wax esters just under 80%, and 2% free fatty alcohol, and 3% dye and triglycerides, and 0.2% free fatty acids. The nature of the fatty acids and alcohols indicated that they were mainly very long chain, saturated types with even numbers carbon atoms. The major fatty acids in canola oil sediment was C20 and C22, while the predominant fatty alcohols in the sediment were C24, C26, and C28. And this was quite different from the sunflower sediments, which contain 99% wax esters, compared to the canola sediments, which are less than 80%. Sedimentation is a physicochemical process involving phase separate transitions. For example, the high melting lipid components are initially soluble in the oil, but crystallize from the liquid bulk, resulting in a haze. While it doesn't represent a health hazard, nevertheless, consumers are less liable to buy vegetable oil with something floating around inside. A typical DSC, differential scanning colorimetry, thermal curves for melting and crystallization transitions for canola sediment are shown in the figure 3 in the top. The canola sediment had a very narrow temperature range with a peak temperature at around 75 degrees, which was much higher than the sunflower sediment due to the fact the canola sediment has greater amounts of longer chain fatty acids and fatty alcohols. The crystallization process shown in figure 4 showed that the heterogeneity of the canola sediment by the peak and shoulder observed during crystallization. X-ray analysis revealed that the crystalline structure of the canola sediment was similar to other waxes, including beeswax and paraffin. The morphology of the sediment crystals is important to its removal from the oil. Microscopic studies showed that the crystal habit of the canola sediment was affected by the cooling rate as well as the concentration. In most cases, as in A, they were needle-like or rod-like crystals, but in B, at a much slower cooling rate of half a degree a minute, you get large, round-shaped and leaf-like appearance, and the structure observed. Now the question asked is, how long does it take for the sediment to appear in the oil? And this one shows various times and sediment levels and temperatures. And this showed when the sediment content was less than 50 parts per million, more than 24 hours was required for a sediment to form at all temperatures. Canola oil sediment containing 50 parts per million became cloudy in 2 days at 25 degrees, while samples with less than 25 ppm sediment remained clear for close to a month. One of the challenges, of course, is to be able to predict this phenomenon so that industry can take appropriate measures to prevent its occurrence. However, it would require winterization, which can be costly, so you want to limit the necessity of having to do this. And there are a number of techniques to determine sediment content in oils, particularly in sunflower oils. These were gravimetric, solvent extraction, and laser-based techniques. We focused on solvent precipitation. Our study showed that the addition of 30 to 40% acetone would bring a quick crystallization of the sediment. So in the analysis, you'd first heat the sample to melt the sediment and cool it to 40 degrees. Then you add the acetone, 40% in a cuvette, and the turbidity developed by placing the cuvettes in an ice bath for a fixed period of time. Then remove the cuvettes from the ice bath, wipe, and you measure them in a chamber of a turbidometer. And here you can see that the turbidity took at least 10, 15 minutes to stabilize to reach a maximum. And if you add 2% phospholipids, you can increase the level of detection by about 23%. So what happened was we then, knowing that, we then developed the method which was to measure. It was the relationship between turbidity in the oil and the sediment was non-linear, and with the added lecithin, it increased the NTU, which is the nephelometric turbidity unit, by 23%, and you could describe it. It can be described by a polynomial equation. And it was a very effective method, and we published that in the AOCS. The sedimentation problem highlighted the impact that non-triacyl glycerol components, comprising no more than 5% of the total lipid components, have on edible oil quality. The main focus of improving the stability of the oils by the plant breeders was focused on reducing the level of the polyunsaturated fatty acids. As a result, the minor components tended to be overlooked. Fortunately, I had a master's student and who needed a project, and she tested my hypothesis and looking at the impact of breeding on the minor components, specifically focusing on tocopherols, following the banning of the synthetic antioxidants BHA, BHT, the stability of edible oils really rely on the total presence of naturally occurring vitamin E or tocopherol isomers. I will present the part of this work conducted on different modified canola oils, although we also included soybean and sunflower varieties as well. Now, in addition to measuring polar compounds, carbonyls, and free fatty acids, we also measured the level of tocopherol and the rate of tocopherol degradation. This slide really shows the fatty acid composition between the 4 canola varieties we looked at. RCA is the regular canola, 7.5% saturated, 57, just under 60% oleic acid, just over 20% linoleic, and just over 10% linolenic. High oleic would have similar saturated, high 74, just under 75% oleic, just under 10% linoleic, and a little lower, 6.7% linolenic. The high-oleic, low linolenic canola oil had a little slightly higher saturated 8%, similar oleic acid, just under 75%, slightly higher linoleic acid, but a considerably lower linolenic acid. And the low linolenic acid would have the 7.2% saturated and would have a similar level of linolenic acid to the high oleic low linolenic acid. Now, this one shows the development of polar compounds, and really the difference there can be divided into two. The top two lines represent low linolenic acid and high oleic linolenic acid canola oil, and you can see the rate of polar compounds was really quite rapid and reaching up to the 30% mark. Well, at the end of the 72 hours of frying, whereas the regular and the high oleic low linolenic canola oil had a more modest increase in total polar components. If we then looked at the tocopherols levels was certainly low in the regular, 565, a little lower in the low linolenic acid, 468, much higher in the high oleic low linolenic acid, and a little higher in the high oleic canola oil. And of course, the alpha and gamma tocopherols, usually twice the amount of gamma versus alpha tocopherol. What is particularly interesting is really the rate of degradation of the tocopherols. And just as the same way we looked at the polar compounds, if you look at the top two lines, which represent, there again, this time the regular canola and the high oleic low linolenic acid canola oil, the tocopherol levels were decreased moderately, whereas in the bottom two, which is the low linolenic acid and the high oleic acid canola oil, there within 10 minutes you almost lost all of the tocopherols were destroyed. So any advantage there was completely lost. If we look at the individual tocopherol degradation rates, you can see from the regular canola oil, the degradation rate was 3.3 parts per million per hour. The high oleic low linolenic canola oil was 7.4. Whereas if you look at the high oleic canola oil, the degradation rate was 50.1 ppm per hour, and for the low linolenic canola oil it was 33. So these were really fast. So definitely was a problem, and certainly, in other words, that we showed that tocopherols are very much responsible for considerable stability of the oil. The fatty acid had been shown to maybe 50% of the stability, and tocopherols probably for the remainder, and this has been shown by other colleagues. So the question now, we had a consortium of companies who were breeding companies who supported us to develop a rapid method suitable for measuring the stability of breeder size oil samples. We decided to use the iAtroscan, and the reason for that is this is flame ionization detection using TLC and flame ionization, and to assess the stability. We had previously used the IATRA scan very successfully for measuring phospholipids as well as for analyzing lipids in cereals as well as quinoa. It has the specific advantage of not requiring very little levels of solvents or samples. You can analyze multiple samples, and you can assess oxidative stability at lower temperatures closer to the ambient. In the top one, you can see you have what are called chroma rods. On this frame, there are 10 chroma rods, and you then spot at the bottom of those rods the particular sample. You then place them in a developing tank with a particular solvent to separate those samples, and then you remove, dry, and then read in the IATRA scan the samples as they go through the flame ionization detector. So it's really thin layer chromatography and using TLC on coated quartz rods. Now these 10 rods which are on the frame, these are very effective because essentially you can take those, and as we did, we looked at the effect of temperature on the oil, put the oil on spot on the bottom of the rods, put them in an oven and for a period of time, separately, one at 45, one at up to 60, 65 degrees, and take them out, dry them, separate them with the solvent, dry them, and then measure them. The silicate glass Vicor contains 96% silicon oxide. It has a specific area of 150 square meters per gram. In other words, the ratio of the volume to the surface area is very high, so the oxidation rate on the individual chroma rods will be high. It'll take a much shorter time to reach the same peroxide value in a SHA-11 test. And the next slide shows the separation of the different components using this developing solvent. You can separate out the polar compounds from the other components. You can measure those if you want. But looking just at those polar compounds, we did that heating time looking at 45, 55, 65 degrees, and followed the a period of time. So these were each of those dots represent literally 10 of these 10 samples. And you can see that the rate of oxidation increased with increasing temperature, both at 45 in a linear way, 45, 55, and 65. So this facilitates a very high oxidizing rate. It only needs literally microliters of the sample, and which makes this method in the order of 10,000 times more sensitive compared to the original titanium method, which required 0.5 grams or 500,000 micrograms. Though again, this method was published in the AOCS. There again, the proposed method allows comparison of oxidative stability of oils. You can use 20 to 30 micrograms of oil. The proposed procedure can be applied for stability comparison at the breeder level to help select the best line for further development. Now, over the past decade, I have been collaborating with a number of colleagues, one of whom is Dr. Usha Thiam-Hollander, and we've been collaborating in examining the phenolic compounds in canola and more recently in mustard, and particularly focusing on canola. And in particular, canola is very rich in phenolic compounds. Cinnamic acid accounts for 72% of the free phenolic compounds, and sinapine, which is the choline ester of cinnamic acid, represents 80% of the total phenolic compounds. And we published an HPLC method to measure that we published in JOCS that I believe was the most highly cited paper in that year. One of the concerns about canola, first of all, it was discovered in 2003, 2004. It has been shown to be a potent antioxidant as well as anti-mutagenic and anti-cancer properties. And it is converted from cinnamic acid by decarboxylation. So the formation of a canola results by decarboxylation of cinnamic acid, which is formed from sinapine, which is the choline ester. However, to produce enough of it, we looked at different ways of enhancing the production of canola. And one of the ways that we looked at, we published, was using a combination of hydrolysis and microwave-induced decarboxylation. First of all, here we have sinapine, which is cinnamic acid attached to choline, and by alkaline hydrolysis, we've also used an enzyme, but alkaline hydrolysis seemed to be more effective, and we produce cinnamic acid and release the choline. For the decarboxylation of cinnamic acid, we used microwave irradiation in the presence of a base reagent, which is this DBU, which is 1,8-diisobicyclodine, DBU, and hydroquinone as a polymerization inhibitor. And using the microwave power at 300 W, we were able to very effectively increase the amount of canola produced. For example, if you look at this table, you can see that after 13 minutes, we had produced or converted 58.26% of cinnamic acid to canola, and we produced 4.16 milligrams per gram. Interestingly enough, and this is looking at the HPLC method, this is sinapine, cinnamic acid, and that is the decarboxylated extract, which is canola. Interestingly enough, a paper just published recently cited the preparation of rapeseed oil with super high canola content and superior quality characteristics by steam explosion. And in their study by Guo and Hang, they produced an oil that contained 2.169 grams per kilogram of oil, the equivalent of the 2001 168.69 milligrams. Our study produced 4.16 milligrams per kilogram, or equivalent to 4.16 grams per kilogram of meal. Sadly, they did not cite that paper, which certainly should have been the case. Very quickly, in finishing up, we did look at crude canola and a canola distillate to look at the stability in a deep frying fat. And using the paranecidine value, you can see that the control, which is the top graph, very rapidly underwent rancidity, and even with BHT was a little more controlled, but the bottom, which is canola and the distillate, they both were much more effective in controlling oxidation. And the distillate contains a whole range of compounds, whether it's Canola, phenolics, phytosterols, and sometimes squalene can all be effective. So certainly it was effective in control as a potential antioxidant. Finally, in conclusion, I'm continuing working with Dr. C.M. Hollander, and we're looking at ways to improve the extraction of polyphenols from canola meal using high pressure and the impact of temperature and solvents. And we published, the last paper was on this area was in the end of last year in Journal of Food Science. And the phenolic compounds have tremendous potential, not just the canola in terms of antioxidant, but also their health-related effects. In conclusion, I've been very fortunate in having a long career that's had an impact in the Canadian agriculture, which I'm happy to have played a small part, and to see the results of this in terms of the production and the acceptance of canola oil worldwide. And I'm grateful to my colleagues, the University of Manitoba, for giving me an opportunity for working in this area as well as many others. And I thank you for your attention. Thank you.